we supply a combination of conductors and dielectrics. Everything from normal laminates, normal PCB laminates, fiberglass reinforced, copper clad, to conductive inks. You have a rear defogger, right, in your car? That's conductive ink. That's printed on. We tend to put PCB materials into certain buckets. And when I started in the industry almost 40 years ago, we had two buckets, flex and rigid. And on the rigid side, we had FR4 and polyimide. Yeah, there was G10, non-brominated fiberglass material. But primarily it was FR4 and polyimide. Polyimide was used for military, high temperature. It's a high temperature material, it still is, it's still around. But then FR4 became the mainstay of the industry. Then high TG FR4s. And that was mostly developed for reliability and survivability of multiple reflow cycles. Nowadays, signal performance has become a big factor, and the transmission lines between components and even in backplanes become a more important factor. You have to consider the entire, transmission network, the entire web of circuitry inside the circuit board. And at high frequencies, things change. So that's when the materials become important. Laminates become important. You could argue they're important at very low frequencies, but let's say at 2 to 5 gigabits, you have to start thinking about them. And then beyond 5, they become very important. And then beyond 10, now the quality of the copper conductor becomes a factor. It's not just length, width, and thickness, it's also how smooth it is. And even at higher frequencies, the grain structure. So people are looking at things like rolled annealed copper for very high frequencies, which traditionally was only needed for flex. And part of it comes from the structure of the copper and the surface roughness. Copper foils for circuit boards are typically made two different ways. You could take sheet stock and roll it down to a particular thickness. That orients the copper grain boundaries in a planar fashion. And then another way is to make electrodeposited foil on a giant stainless steel drum and plate the drum and peel off the foil. Traditionally, it's been easier to make thinner foils electrodeposited and thicker foils in rolled annealed because you're going one way or the other, right? With rolled annealed, you're going thinner, thinner, thinner. In electrodeposited, you're plating up in thickness. So you can stop that process earlier or speed up the drum for thinner foils. Very thin foils are hard to make in both technologies because you can actually break the foil in mid-process, which is very, very bad. Well, for mechanical, think of the rolled annealed foil, the grain structure of the foil as being pieces of overlapping slate. So when you bend the foil, you're not cleaving the grain boundaries the same way you are in electrodeposited, where you have a columnar grain structure. Columnar grain structure, you bend the foil. Now the foils have gotten much better, even the electrodeposited for flexing, but they're still not as good as the rolled annealed foils. When it comes to high frequency, it's the same thing for a similar reason. The rolled annealed tend to have tighter surface structures and smoother surface structures. So that's better for high frequency. When you have rough copper, you start radiating some of the signal energy into the dielectric. Actually, it happens, regardless, but the smoother the copper, the less of the energy is going to the dielectric, the more of it is staying in the actual copper. It's minute, but it adds up when you're dealing with very high frequency. When we talk about transmission lines and PCBs, we're talking about typically high-speed digital strip line construction. So you would have a reference plane, your signal reference plane. You could also have differential pairs, but typically we're talking about a strip line construction where you have a plane on both sides of a signal trace. That's your high-speed digital transmission line. I mean, from a very high level, the difference between RF and HSD is HSD or high-speed digital, signals are staying in the board. RF, your signals are coming in and out, right? You're trying to get the signal out of the board. In fact, if you go to some of the Altium talks, you'll hear about some of the things you do to prevent an HSD board from radiating energy out, which you don't want for a lot of different reasons. So high-speed digital, we want to keep the signal in trace. We want as low a loss as possible. We want as fast a rise time as possible, and you do that by making the transmission line, high performance. And that's where the materials and the copper are important. We'll talk about high-speed materials. So FR4, which is a flame retardant epoxy system. These days, they're all multifunctional systems, which means there's a lot of cross-linking between the epoxy monomers. They have good thermal performance. Those were the mainstay for many, many years. There was a change in 2006 when lead-free assembly started to become popular and when RoHS went into effect. So the materials had to be more thermally robust. All the materials can survive soldering for a short time, but when you pump the assembly temperatures up 50 degrees to work with SAC 305 alloy, the catalyst had to change, and most of those systems are lead-free phenolics now, or what we call phenolic-cured epoxies. Those actually don't perform as well as the old epoxy systems in high frequency or high speeds. Not that the epoxies were great, but they weren't as bad as the phenolic-cured epoxies. So that really showed a need, because right around that time, speeds started to increase. So people started coming out with other resin systems. So epoxy cyanate ester blends, PPO blends, so polyphenol and oxide blends, Teflon-filled materials or PTFE-filled materials. All these other materials start coming out that lowered the signal loss, or what we call the loss tangent or dissipation factor of the materials, so they perform better at high frequencies. And I don't know if you've ever seen an eye diagram, right, where you have a digital signal. When the eye closes in, that's because the rise time gets very long. You can actually get to the point where the system won't operate because too much of the energy is going into the dielectric material and not staying in the trace. Now, some people would say, well, the energy is in the dielectric anyway, and the trace is just a waveguide, and that's true. But really the energy is coupled between the trace and the reference plane or the return path. The energy is not being consumed in the dielectric. Really, that's the difference. That's where these low loss materials come in. And these different materials have different properties in terms of loss. They also have different cost point. Depends on what you need out of your design. I think the folks that work in RF already understand the need for low loss materials. Well, Rogers materials have been out for a long, long time. We have some materials that compete in that space. I think it's the Highspeed digital folks that they go beyond that certain threshold, whether it's 3, 4, or 5 gig, and they need more performance. They'll go to something like a 408HR, which is an isolar product that gets them a step beyond on FR4. So, for example, regular FR4 might have a loss tangent or dissipation factor of 0.018, maybe 0.020. A lead-free phenolic might be 0.020 to 0.025, right? And then you get to something like 408HR, which is 0.009. So it's substantially better in loss. But then you can go to other materials that are even lower in loss, 006, 004, 002. There are even some materials that are playing the 001 space. Typically, those are Teflon-based materials. By the way, Teflon is a very low-loss material for high frequency, low decay, low loss. But it's also very difficult to make a PCB out of for a lot of different reasons. It's a thermoplastic. It's very flexible, but it's not very mechanically strong. So you have to reinforce it with things that take away from its performance. And you have to use rough copper, which takes away from its performance. So there's a lot of different trade-offs going on at the same time. That's another thing that's probably important, in this discussion is, these are all composite materials, right? So there's a lot of different factors. Each part of the composite brings both a function and a caveat. That's the problem with Teflon. It doesn't stick to things, right? But, it does have some good high-frequency properties. People are overly cost conscious and they use a material that doesn't perform. And I've also seen where someone uses a more expensive material than they need. So I've seen it both ways. I've also seen a PCB shop process the material incorrectly and take away from its performance. And one example is they bond treat the copper layers. After they print and etch the circuit pattern, they'll do a bond treatment. And if they overdo the bond treatment and over roughen the copper, they'll take a lot away from the performance of the material. Well, so the bond treatment chemistry is designed to roughen the copper, so when you bond all your layers together, the resin is something to stick to. If you do that excessively, and I'll give you an example, we typically talk about copper roughness in RZ. It's a measurement of roughness in peak to valley. It's an average peak to valley. Standard copper might have an RZ on the non-drum side of 6 to 8 microns. Low profile copper is 5 or below. Very low profile copper, or what we call HVLP copper or VLP2 copper, is around 2 to 2.5 microns RZ max. So it's very smooth. That gets bonded to the core material. The core material goes to the PCB shop. They etch their circuitry in it. And then before they laminate all their layers together, they'll bond treat that copper with their process. And that might put on an RZ of 1.5. But if they overdo it, they could be 3 or 4 microns. So they could over roughen the copper as part of the bond treatment and then take away from the performance. Copper foil isn't just copper foil. After it's made, it goes through some secondary treatment processes where a dendritic layer is actually electroplated on. These little tiny nodules are plated on. And the idea is to make it bondable. When you do your assembly, you don't want all the layers to blow apart, right, or burst apart. You want the resin to stick to the copper. You want all your circuitry to be well encapsulated. You want it to be reliable. There are other treatments on the copper as well. Some of them have to do with keeping the copper of good quality until it's imaged. And what we call imaging is the printing and etching process. There's another treatment on there to prevent the flame retardant in the resin to react with the copper. So there's a lot of functional layers that are added to the base copper foil for it to do all the things it needs to do. Well, we like to team up with the fabricators. In other words, when the designer, certainly the design community is one we're trying to reach, so they have the information up front. But we're also trying to make sure the fabricators have all the information they need for the designers they work with. So it's collaborative.
Thanks for watching. To learn more about how Royal makes printed circuit boards in as little as 1 day, or if you would like to use our free Design for Manufacture service, please visit royalcircuits.com.